All right, section 2 of chapter 9 talks about functions of exponential order. And by definition, what does this mean, right? So this function f of t is of the order of g of t, and we write that as f of t equals a big capital O of g of t, if there exists positive constants m and n such that the absolute value of f of t is less than or equal to m times g of t for all t greater than n. So it's like bounded, right? And we say that f is of exponential order if f of t is of the order of e to the at for some constant a. And so that's what we're interested in is functions of exponential order. All right. And basically what it's talking about is that the rate of growth of this function is no faster than that of an exponential function. And if that's the case, then we'll see some results that end up happening. All right, so let's do, I'll write this part that f of t is of the order of g of t if there exists m and n positive constants, such that, that's what we care about, that the absolute value of f of t is less than or equal to some constant times some function, and that's for all t greater than n. And we say it's of exponential order if that function inside exponential order if f of t is of the order of e to the at for some constant a. All right, so let's we're going to show that cosine of t, that's your f of t, is of the order 1. All right, so we're going to take this definition. F of t, well, that's cosine of t. Yeah, and we know cosine is bounded, right? We know that cosine is between -1 and +1, and so this is absolutely bounded less than or equal to +1. And that's true for all t, right? For all t, cosine is always bounded less than 1. Well, the absolute value is less than 1. And so definitely it's true for t greater than 0. And so when I'm looking at these guys, all right, well, I really want to show that it's of exponential order is really what I want to show. So what we could say is that we could say that 1 is like e to the 0 t, yeah, and it's like 1 times e to the 0 t. So now your g of t is e to the 0 t, and your capital M is 1, right? And so for this guy, that means that it would be M is 1 here. Your N is greater than 0, right? And your A is 0 since e to the, right, that's your A value there. All right. So cosine is of order 1, and it is of exponential order since if a is 0, then e to the 0 is 1. All right, let's show that e to the 2t over t plus 2 is of the order of e to the 2t. Okay, so absolute value of your function would be the absolute value of e to the 2t over t plus 2. Okay, so now if I'm looking at for t greater than 0, t is greater than 0, well then you've got a positive number and then over a positive number. So I can drop off the absolute value symbols. And I know that this is definitely less than or equal to e to the 2t over 1. Remember, t is greater than 0, so um, the, the smallest this would be 2 something, right? And that's just e to the 2t. And we did it, right? And this is for all t greater than 0. So your m is 1, because there's 1 in front of there. Your n is, I'll put n is greater than 0, and your a is the on the exponent there. So a is 2. All right. How about another one? How about that the function t is of the order e to the t? So again, taking the absolute value of this guy. Well, if t is greater than 0, then that's just t, which t is definitely less than or equal to e to the t for all t greater than 0. Yeah, if t is greater than 0, then you've got all of these guys that it's definitely less than that. And so um, you're in this case, so it's of the order, we got it, which means your m is 1, your n is greater than 0, and your a is 1 in that case. All right, one more. Let's show that e to the 2t plus 1 over e to the t is of the order of e to the t. All right, so absolute value of f of t would be the absolute value of e to the 2t plus 1 over e to the t. And for t greater than 0, this we can drop off the absolute values. E to the 2t is always positive, e to the t is always positive. You're adding a 1 there, it's a positive. So that is true. Now, I want to show that it's of the order of e to the t. So this is definitely less than e to the 2t plus e to the 2t over e to the t. Yeah, since e to the 2t is definitely greater than 1 for larger than 0. And so that gives me a 2e to the 2t over e to the t, which gives me a 2e to the t. So for this one, your m is 2, your n is greater than 0, and your a is 1. And so we've shown that all 4 of these functions are of exponential order. Why do we care? Well, I got to give you a definition first and then a theorem. So what does it mean to be piecewise continuous? F is piecewise continuous on the interval from 0 to infinity if f is piecewise continuous on every interval from 0 to b, where b is greater than 0. So what does that mean? It means that f has a finite number of discontinuities with no vertical asymptote. I guess that's worth writing. F has a finite number of discontinuities with no vertical asymptote. All right, so we can say that it's piecewise continuous from 0 to infinity. So on this interval, if f is piecewise continuous on every of these small little intervals from 0 to b, right? Okay, so got those 2 definitions. You know what of exponential order is, you know what piecewise continuous is, and so that leads us to the theorem of why do we care? Let f be piecewise continuous on 0 to infinity, right? With f of t being of exponential order. Right, so f is piecewise continuous and it's of exponential order for some constant a. Then the Laplace transform exists. At least for s greater than a. All right. So, yeah. All right. So this is a sufficient condition, not a necessary condition. That makes sense. It's not that this has to happen. The Laplace transform can exist if it's not true, but this is a sufficient condition to know that it exists. All right. So let's look at example 5 that says, without actually computing the Laplace transform, we're going to show that it exists. So without computing the Laplace transform, show that it exists for the indicated values. The indicated values of s. All right, so the first one we're going to do is f of t equals cosine of t for s greater than 0. All right, so first we got to talk about, is it piecewise continuous? Is cosine of t piecewise continuous? Well, cosine is continuous for all real numbers. So it's continuous for all real, not just on this interval from 0 to infinity. So it's piecewise it's continuous for all real numbers, and so it's definitely piecewise continuous on the interval from 0 to infinity. So yep, got that one. And then it needs to be of exponential order. But we figured out that cosine was of exponential order. Well, it was of order 1, which we had said was of exponential order because it's e1 is just e to the 0t. And this is from example 1. I'm going to do all the work again. All right, so my theorem says if it's piecewise continuous from 0 to infinity and of exponential order, then the Laplace transform exists. And that's all they're asking us to do today. Yeah, we'll apply it in a later lesson, but today it's just, what does exponential order mean? What does piecewise continuous mean? Does the Laplace transform exist given those two conditions? All right, how about same thing? Don't compute it, just does the Laplace transform exist? And this is e to the 2t over t plus 2. And this is for for s greater than 2. Okay, so what do we know about this guy? Well, we know that this e to the 2t over t plus 2 is discontinuous. Right, we've got a vertical asymptote at t equals -2, right? But we don't care about it over at -2, but it's piecewise continuous on the interval from 0 to infinity, since -2 is to the left of 0. Yeah, so our asymptote is at -2, but on this interval from 0 to infinity, it's definitely continuous. All right. The other thing we got to do is say that it's of exponential order, and e to the 2t over t plus 2 from example 2 is of the order e to the 2t from example 2. No? So therefore, the Laplace transform exists. One more. How about if f of t is t for s greater than 1? All right, so t. Well, y equals t. That's just a straight line going through the origin, right? So this is definitely continuous for all real numbers. And so definitely piecewise continuous on 0 to infinity. And then from example 3, we found that t is of the order of e to the t. And that was from example 3. Check. And so the Laplace transform does exist. All right, we'll see in the next, in a coming up section, why, right? We even care about this, but I'll give you a little hint that we have a theorem that every solution to P of D operated on x equals 0 possesses a Laplace transform. And every derivative of every solution possesses a Laplace transform. I don't know why I wrote all this out instead of showing you the note paper, but oh well. There you go. All right, so we're going to end up using this, right? We're going to end up using it to solve not exponential, but differential equations. All right, hope you all are having a fantabulous day. Doo-doo-doo.